Hallo, it's dumplet here. Here's an item on number theory. Find the last two digits of 13 raised to 13 raised to 13 raised to 13. Now credits to the PUMaC. It's a Princeton University Math Contest. It's an altered problem, but thanks to them for the inspiration for this item. Now the original problem, the OG problem, instead of 13s, they used 17s, so you can also try that out. Anyways, as usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now let's focus on the version where I have stacked exponents, I have stacked 13s. Now, it's very common for competitions to have an item that's calling like getting the last few digits, getting the units digit, and it's typical for you to use a modular arithmetic. Now, for last two digits, we would take mod 100 because whatever this number is under mod 100, it's going to give you the last two digits. Now here's something nice to memorize, which is the lambda of 100 is 20. Now the lambda here is the Carmichael lambda function. It's also called the reduced Euler's, it's called the reduced totient function. And this tells us that, well, since 13 and 100 here are relatively prime, I would have 13 raised to 20. It's going to leave a remainder of 1 when I divide it by 100. So it's 1 mod 100. And with this motivation, I would try to take the exponent over here, so 13 raised to 13 raised to 13. I would want to get it under modulo 20 because whatever this is, I can replace this exponent simply with this question mark over here. But, well, this under mod 20 is not that trivial, so we would do another step. Let's try to take the exponent, 13 raised to 13 over here, and we would want to check it under phi of 20. Now, phi here is the Euler's totient, and you can get that phi of 20 is going to be equal to 8. Now 13 raised to 13, it's going to be something we're going to check it under mod 8, and it's not that trivial, but with the help of this one, phi of 8 equals 4, again the Euler's totient, we can get that 13 raised to 4, it's going to be 1 modulo 8. Now 13 raised to 4 being 1 modulo 8, it's a very nice thing because I know that 13 raised to 13 I can make it into 13 raised to 4. I'm going to cube this and I'll have another 13 over here because I can split using the laws of exponents. Now since 13 raised to 4 is 1 modulo 8, I can simply replace this 13 raised to 4 with 1. Now obviously 1 cubed is just 1, so whatever is inside is just equal to 13. Now 13 modulo 8, it's going to be equal to 5. So we're trying to, we're getting there. Now I know 13 raised to 13 is 5 modulo 8, so I'm going to go back. This thing is just saying 13 raised to 5 modulo 20. Now, here's a little bit of a part we have to actually expand. Well, 13 raised to 5, I can write it as like 13 squared times 13 squared times 13. So it's like 169 squared times 13. And then 169 under modulo 20, it's going to be equal to 9, so 9 squared. Now 9 squared is 81, and 81 is 1 modulo 20, so this is just actually equal to 13. It's kind of nice that we're able to simplify. So we know that 13 raised to 13 raised to 13 is 13 modulo 20. So all we have to do right now is just change this entire stack of 13 into 13 because the exponent under mod 20 is just 13 anyways. So we're now doing this. Now this part, again, it's a little bit of an expansion here. But here I have something nice, 13 cubed, that's equal to 2,197, and that's going to be equal to negative 3 modulo 100. So again, the 13 raised to 13, by laws of exponents, I can make 13 raised to 13 equal to 13 raised to the 4th power, sorry, 13 cubed raised to the 4th power, and then times the 13, that's what you see here over this part. Now 13 cubed, it's going to be negative 3, that's why you have the negative 3 raised to 4 over here. And the 13 here is just the same as the 13 here. So all we have to do, again, we're just simplifying stuff via modular arithmetic. Negative 3 raised to 4, it's going to become 81. So again, this part we have to do it by hand. 81 times 13, that's going to be equal to 1,053. And, well, having this number is kind of nice because we're almost done. Last step is just to take 1,053 and divide it by 100. The remainder is 53. And since everything can be traced back to the given, we started with 13 raised to 13 raised to 13 raised to 33 raised to 13, and we did some modulo modular arithmetic, and we've made our way to 1053 and ultimately getting into 53. So this given under modulo 100 is equal to 53. And since we're taking modulo 100, the 53, it's going to be the last two digits of the given expression. And that's our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!